of Ampere. We're on to Ampere's law today. French physicist, 1775 to 1836. Credited with the discovery of electromagnetism. Well, only in the sense that charges in motion made magnetic fields. We're coming more to what I would call the proper electromagnetism next week. I mentioned that Maxwell was an incredibly brilliant mathematician, and Ampere also was a mathematical genius. It's said that by the age of 12, which is mentioned here, he said every single number between every single prime number between 1 and a million is a personal friend of mine. So if you went, if you'd asked the 12-year-old Ampere, is 933,721 a prime number? He could have answered it immediately, and if it wasn't prime, he could have factored it instantly. So again, we're dealing with somebody who was a very clever boy. His personal life, however, was filled with tragedy. His father, a wealthy city official, was guillotined during the French Revolution. His wife died young. He died of pneumonia at age 61. His judgment of his life is clear from the epitaph he chose for his gravestone. Happy at last. Oh dear. How sad. Come on, let's have a big sigh for the oh. So, poor old Ampere. Of course, we could be harsher, and if we'd met the kind of 50-year-old Ampere, just said, for God's sake, Andre, get a life, But we're dealing, of course, always in physics. It's part of what makes it difficult for us. Obviously, we're dealing with the life and works of people who spent their whole lives working on problems when they were brilliant mathematicians, and we have to summarise it all, in a couple of lectures. Just before we move on to the details of applying Ampere's law, I'd like to briefly review what we did last week. In lecture 1, we took an overview of the Maxwell equations, and I pointed out that when the fields, the magnetic field and the electric field, are not changing with respect to time, we appear to get these two different subjects of electricity and magnetism. And what I concentrated on, I mentioned at the end of the lecture, all we've done is abstract these differential equations from the integral forms of the laws that you studied last year. Well, that's already a very, very big step. And I'll just again review how we did that. The lectures recordings are now up on the VLE, so if you missed any of the lectures, you can catch up either via the notes or via those recordings. And just to stress, Gauss's flux law of electrostatics, you've already seen in EM1, and I went through very briefly again last week, that's equivalent to Coulomb's law. So this is the experimental fact. We then had the pure mathematics, which applies to any vector field, and so by applying it to the electric field, we saw that we could abstract Maxwell's first equation. And I was emphasising these local laws, differential laws, are much more powerful than the general integral laws. And in particular, this equation is true at every point in the universe. On Friday, we did a very similar thing for Ampere's law of steady currents. So again, this is the integral form of the law that the circulation of the magnetic field around any closed loop is mu0 times the current through the loop, where this is the current density in amps per square metre. And we can obviously, if we have that parallel to n, so in a fine wire, the line along the wire is this way, the current density is this way. So of course we just have the magnitude of J is J dot n, and if we integrate over the area of the wire, we multiply by the area and we get the total current I. Again, that is the physics, that's the relationship of the field to the source. The source is the current density and B is the field. Then in this case the pure maths is Stokes' theorem. This is true for any vector field, so we can certainly apply it to the magnetic field, and therefore we can abstract this differential equation. Now notice there is a piece missing from this equation, and I'll prove next week that, and this was one of the very powerful reasons why the differential equations are important is that in its differential form it became obvious to Maxwell, it's certainly, unless you're a real genius, probably not obvious to you at the moment, that this equation isn't true if electric charge is conserved. Incidentally, Christian, this afternoon in your quantum mechanics, will be talking about the conservation of probability density, local conservation of in terms of quantum mechanics, and that will have quite a strong bearing on lecture 9 that I'm doing on charge conservation. So let's just leave that up at the moment. This is Ampere's law. This is Ampere's law. And again, we're going to use both forms of the laws. Tomorrow I'm going to come much more onto the consequences of the differential law and re-express it in terms of the so-called vector potential. Today I'm going to look at some consequences of the integral form of Ampere's law. So, excuse me, the first thing I'll do is I'm just going to rewrite this. I know we've had that as the last in the last lecture last week, but I'd like to just pop it back up on the board. So the integral form of Ampere's law is that the line integral of the magnetic field around any closed loop is equal to mu naught times the surface integral of any surface bounded by this loop gamma of the normal component of the current density integrated over the area of the loop. So that's straightforward because you did that last year, and indeed, if I can actually get the right blackboard, for a fine wire, and obviously this is a very common case, we want to analyse the magnetic field around a current carrying wire, we have that this same integral of the magnetic field around this closed loop is equal to mu naught I, where I is the current through the loop. Again, as I said, for a fine wire, imagine that we've got, there's our fine wire blown up, the current is coming out towards you, the normal is coming out towards you. So of course, if this is representing, and we're assuming that the current flow is uniform everywhere inside the wire, so that it's a constant flow, well, J dot N is just the magnitude of J, again often just abbreviated to J, and of course if the current density is constant over this this surface, then integrating over the area I just have to multiply by the area, and J times the area, where this is in amps per square metre, if I multiply that by the area in metres squared, of course I just get the total current coming down the wire. And indeed, this is precisely the form in which you would have studied Ampere's law last year. So let's make that equation 4-2. Now, so that's the basic law. Oh, what a beautifully clean blackboard. I'll move over. So, to emphasise at the outset, there are very few practical problems that can be solved with Ampere's law. You see, what we're saying with Ampere's law, again, I'll come back to that general view graph. Obviously, this is the law. This is the integral form. Is that we've the view graph shuffling monster's been at work again. Anyway, the view graph's been up a few times. In general, to solve a magnetic problem, we also need to apply that the divergence of the field is equal to 0. But in certain very high symmetry circumstances, we can just use Ampere's law on its own to get the answer. And there's really only two. There's the long straight wire and there is the solenoid. And I'll be doing both of those in this lecture. So first of all, let's do the long straight wire. And first of all, we're going to use the experimental fact that if we have a long straight wire, the magnetic field lines go round it in circles. And again, we're using this idea of symmetry. So let's say this is a long current carrying wire and the magnetic field lines are going round it in circles. Again, we're using the argument, there's no reason as it circles round that it should have a different magnitude at this point, or this point, or this point, or this point. It's just circulating round and its magnitude must be equal at each point on this circle. So again, the integral that we've got to do on the left-hand side of Ampere's law is extremely simple, because ds, as we go round the circle, is always parallel to b. So b dot ds is just b ds. B dot ds, they're parallel to each other, so the scalar product is just their magnitudes multiplied by each other. So let's take exactly the first of the cases that we can solve with Ampere's law. A is the field outside a long straight wire. So this is case A. Got the field outside a long straight wire. It's because B is parallel, again a standard abbreviation, for parallel to ds, we have B dot ds is just B ds. And again, usually this is just abbreviated to B ds, rather than always writing the magnitude of the vector B. We just write B for its magnitude. And then, so this integral on the left-hand side, this line integral just becomes b ds. So left-hand side becomes b ds. But then likewise, because of this, again, it is a symmetry argument, we are using, some kind of intuition, a sensible intuition, and one that's experimentally true. I mean, as you go round the wire, the magnetic field doesn't, become 1 Tesla here and then suddenly 3 Teslas here and 5 Teslas here and so on. It's constant. And so this comes outside the integral, and the integral becomes B integral ds. And everybody can say, well, if I integrate ds around a circle, I get 2 pi r. It's just the circumference. So the left-hand side then just reduces simply to B times 2 pi r. We've already seen that the right-hand side is mu naught I, so we immediately get this very, very nice simple solution that the magnetic field, it's circular, and its magnitude is mu naught over 2 pi, usually put the constants together, I over r. So let's make this 4, 3. So we've already solved the long straight wire, and indeed that's the hidden bit of the view graph. Let's go there to the answer. So again, what's written up on the view graph there is sort of the order in which we learn things. Probably school physics, we learn, B is equal to mu naught over 2 pi I over r. Incidentally, how many people did the Biot-Savart law experiment in labs last year? How many didn't? It's about 50-50, but you can, if you didn't do the experiment, you can certainly ask one of your colleagues to verify. Indeed, the precise point of that experiment was you showed B is linearly proportional to the current in a range of about 1 to 10 amps, and you, by measuring the magnetic field with a Hall probe, you also show it's inversely proportional to the distance. Note this is the first power of the distance from the wire, and by doing these experiments, you were also able, and if you did the experiment well, to get a very good answer for mu naught as well, the permeability of free space. So this is experimentally true, and indeed that's the way we learn it at first. We then, in a more sophisticated way, look at it in this integral form, and we've seen that it's also equivalent to this differential form for the curl of the field. Question: in this, where does the curl point? In this diagram, where does the curl point? Come on, the worst you can do is make a fool of yourself on lectures that are going up on YouTube. You know, I mean, that's the worst. That's the worst it can get. You know. So, any answers? Yes. Good try. No, it doesn't point away from the wire. Think vector equation. What's on the right-hand side? The current density. Where's the current density pointing? Oh, you're shy. Come on. Where's the current density? It's along the wire. Of course it is. The current's flowing along the wire. The current density is along the wire. It's a vector equation. The vector on the left is equal to the vector on the right. Now, I can multiply by a scalar. Multiplying by a scalar, I can change the length of a vector. Can I change its direction? No. Good. That was more like it. Got several people on that. So the curl points along the wire. Yeah? The circulation is around the wire, the curl is along the wire. Remember, when we did Stokes' theorem, it's the normal component of the curl that we consider in Stokes' theorem. And a lot of people get confused with this from the outset. The circulation, this integral of B dot ds, line integral, around the wire, the circulation is around the wire, but the curl, which is necessarily parallel to J, is along the wire. It's normal to the circulation. So again, you know, that's something to bear clearly in mind. So this is the answer to the question, what's the field outside? B, the second thing we can solve, is the field inside a long straight wire. And note, both these calculations apply to electron and ion beams. This current density doesn't have to be confined to a wire, it can be a beam in space. And you know that these beams are incredibly important in modern particle physics. You have a beam of protons circulating this vast many-kilometre track at CERN, and of course, the scientists who guide these have to be rather careful to consider the magnetic field that they produce, which of course interacts with the magnetic field of the various multipole wigglers that accelerate the beam, and so on. So let's consider first of all that the current is still uniform, and then it suddenly drops to zero. So first we'll do it for the wire, where we just say there's a uniform current density inside that then suddenly drops to zero. So if you like, for a wire, the current density, and again we're going to treat this, particularly for an ion beam, when I do a slightly more sophisticated example in a few minutes, well, let's let this be R, be the distance from the centre of the wire. Now, our first calculation, remember now the wire's just coming out of the board towards you, we've done a calculation which applies to, let's let that be a kind of, a fixed radius of the wire. We've done a calculation which applies when R is greater than A. In other words, all the current was passing through this Stokes loop. Now, however, if I want to calculate the current inside at some distance R which is less than A, well, of course, if the current is flowing uniformly through the wire, and incidentally, it's a very good approximation. I mean, basically, inside a typical conductor, say a piece of copper, the current density is constant, more or less up to one atomic layer of the surface. The surface electronic states are slightly different, but it's not at all, for a wire, a bad approximation to say that the magnitude of the current density is some constant value to the edge of the wire and really drops to zero precisely at R is equal to A. But if we're inside the wire, again, we can solve this with the kind of way that you did it last time. Now, the current passing through the loop is the total current times pi r squared over pi a squared. Yeah? There's only this, this is the cross-sectional area of, this is now our Stokes loop gamma, and the surface passing through it, well, not all the current's passing through it, some of it's outside. So it's not bounded by the loop gamma, and the ratio of the current coming through this loop to the total current is the total current times pi r squared over pi a squared. And of course, the pi's cancel out. So we have this as this is now the right-hand side of Ampere's law. Yeah, this is just the amount of current that is passing through this Stokes loop. Well, the left-hand side is the same, isn't it? I mean, all the arguments we use, here's my B field, it's still circular by symmetry, and it's still parallel at this point ds by symmetry. So all those arguments apply exactly the same. So I've clearly got that now B times 2 pi r is equal to I times r squared over a squared. Yeah, so that is now an entirely, again, straightforward piece of algebra. The B, therefore, is equal to, excuse me, what did I miss? Ah, thank you, yeah. The right, oh dear. When these lectures go absolutely viral on the internet, I go, oh no, I'm going to edit that out. Actually, I was thinking of doing a bit of editing, but not so much on the visual as on the audio. Because I thought, well, you know, when I tell a joke that just, of course, just drops like a lead balloon and there's complete silence, I've just said to Matt Cornick at the AV Centre, you know, oh, just put in a little medium-sized chuckle here. And, you know, or big belly laugh here, really turn the volume up, make them think the students are really enjoying the lectures. You know. But, so mu naught was missing. My usual excuse, oh, you always make mistakes when you're close to these big equations. And of course, we've got the mu naught over 2 pi again. That's coming out front. Let's actually, I'll tick it off so I don't miss any terms when I do this very elementary algebra. I then have got r taken over to this side, cancelling with the r squared, and I've got r over a squared. And there's my answer. Let's call it 4, 4. Yep. And yes. Of course, that was deliberate, just to check you were still awake. Medium-sized chuckle. Mu naught I over 2 pi. And so notice now that the field increases linearly with distance from the centre of the wire. So overall, combining these two cases for a straight wire, we can plot B versus R for any distance. And clearly, it goes like this. Remember, I'm being very loose. We know that B has got direction. It's a vector field. So it's always going around the wire. This B just represents its magnitude. And its magnitude goes up to some maximum value at the surface of the wire. And then, beyond R equals A, it falls away. So this is proportional to R and proportional to 1 over R. And of course, those two formulae give the same at the surface of the wire. because when r is equal to a, this just becomes 1 over a, and of course with our previous formula, when r is equal to a, we get the same. And that's what's called the field being continuous at the surface. That relates to the problem question I set you. Sorry about the problem questions. There's some problem with the VLE not getting loaded up, but I think, you know, with all this week to do them, they're quite easy, the first two problems that I set, and you should still have plenty of time. But now, let's consider a slightly more sophisticated example where the current density is not simply constant. It is experimentally inside a wire, but let's say we've got an ion beam. I haven't worked at CERN, but I've done quite a lot of work at the Rutherford laboratories, and there a straight linear accelerator takes protons up to about you don't need these very high energies, just about 0.9 the speed of light. You smash them into a heavy metal target to make neutrons. But again, you've got to know the magnetic field, because you know that influences how the beam spreads out. You want it collimated. So now our model, let me just draw it again. Now imagine that there's an extremely intense proton beam heading this way. Whoa, watch out, Aaron, it's coming your way. So it's, but now you can imagine, because of the electrostatic repulsion, or electromagnetic, but we've only done electrostatic so far, there's a lot more ions at the centre, and then the beam just gradually thins out. It wouldn't be perfectly uniform, and then the number of protons suddenly drop to 0. So this model actually wouldn't be that good. Somehow or other, the current density will drop away gradually from this is the centre of the beam, this is r is 0. It will gradually drop away. You know, it might be linear, it might be square, whatever. Let's not consider the details, but I will make a model. So let's now consider a model for an ion beam. Plausible model, maybe J is equal to J. Again, I'm using this loosely. We know it's a vector, but I'm just writing its magnitude. This is the magnitude of J as we go out from the centre of the wire. Now, I'm still assuming a symmetry with respect to angle. I'm now no longer assuming that J is constant with respect to R, but I am assuming we'd have the same number of protons at any phi. It doesn't matter where I take the angle, it's still circularly symmetric. The electrostatic should spread it out, but they shouldn't spread out more to the North Pole than the South Pole or along the equator. So we're just looking at J being a function of R. Let me just maybe write that explicitly. Excuse me, J of R is some J naught into 1 minus R squared over A squared for J is, excuse me, for R is less than A, and J is 0 for R, excuse me, greater than A. So again, to make the integration easy, we will cut the beam off as if it really did have an edge, but we'll allow for the fact that it's falling off, and in this model, it's falling off as the inverse square of the distance. So in other words, the beam is coming towards you. It's circularly symmetric in the sense that there aren't more protons here than here, or here than here, but as R goes from the centre, the current density is falling off. And of course we would interpret this J naught as the current density at the centre of the beam. Obviously if R is equal to 0, this just becomes J naught. So now the right hand side, excuse me, it's running out of chalk here, is slightly more difficult to evaluate, but not much. Yeah? Now the right hand side is, and of course we're going to do this integration in circular polar coordinates. It's got circular symmetry. It's precisely why we bother learning things like circular polar coordinates to make these problems easy. Well, we've got to get J dot N dA. Yeah? But again, same argument. There's still, in this case, j is still pointing this way and n is still pointing this way. So this j dot n is just the magnitude of j dA. And this will be equal to, let's write explicitly, j of r. It is a function now. You see, we can't take it outside of this integral. It's a function. It's a function of distance from the centre of beam. But we know r dr d theta. Double integral over r and theta. Yes? Sorry, I've written the angle here as phi and the angle there as theta. Some angle theta as we go round. Well, because it's circularly symmetric, the angular integral just gives me 2 pi. This isn't a function of theta, so the angular integral gives me 2 pi, but then I've got the integral of j of r dr. Yep. Now I've got 2 pi times the integral. Again, the j naught comes outside. That's constant. That's just the value of the current density at the centre of the beam. And then I've got 1 minus r squared over a squared r dr. Now, I know that you can integrate much more difficult functions than this. I've got r. Incidentally, despite your sophistication, I have seen people forget to put this r in and just integrate 1 minus r squared over a squared times dr. It's r dr. So, of course, I've got to integrate r minus r cubed over a squared dr. Well, even I can do this one. If I integrate r, I get a half r squared. And if I integrate r cubed, I get a quarter r to the 4th. Yep. And then I've got to, I've been very naughty, I've left my limits out all the way. Of course, I've got to integrate from 0 to a. Or if I want the whole thing, no, but and again here, this is, sorry, it's very naughty of me. I should use a different, maybe prime the variable and integrate up to some distance r which is inside the beam. Again, I want my Stokes loop to be inside the beam. I want to know the magnetic field inside the beam. I've got to integrate this from 0 to r, which gives me, no, it's rather, as I say, I should really have primed these variables. This is now equal to r squared over 2 minus r to the 4th over 4a squared. So, running out of blackboards already. Haven't even started on the solenoid yet, but no, well, plenty of time for that. And of course, the left-hand side, again, is the same. We've got all the same arguments that we've used twice. We don't need to redo it. We know the left-hand side is b times 2 pi r. We know the right-hand side is mu naught times the current. The current is this integral up to this variable distance r, which is equal to r squared over 2 minus 4 over 4a squared. So you see, we've now, of course, there's a simple cross multiplication, but we've now solved the problem of the magnetic field inside this inhomogeneous ion beam. Yes? Sorry? Thank you. I've missed every constant in this. If I was marking this as an exam, kind of, I'd have got about 2 out of 7 for this calculation if I was marking it myself. Oh, groan. Thank you. I've left out the 2 pi j naught throughout, which you can neatly throw into your notes here as 2 pi j naught. How many mistakes can you... I really am going to have to record this one absolutely from scratch again. Yeah. I think I've got it right eventually. The 2 pi's are just going to go. And b is equal to mu naught j naught, thank you, times r over 2, again just dividing through this r, minus r cubed over 4a squared. Hooray, got there at last. So you see, this is very nice that we've got we can calculate with this integral the magnetic field inside an ion beam, which is, as I say, it's a little bit step further than what you might have done last year. Incidentally, what is the magnetic field outside this inhomogeneous ion beam? Without doing any calculation, outside the ion beam. It's just the r to the minus 1 field. Once you're outside the ion beam, all of the current is passing through. It's just the total current in the beam is the only thing that counts. Once you're outside the ion beam, it doesn't matter how inhomogeneous. The distribution inside the ion beam could go, it could be like some really weird, complicated function. If I calculate at R outside, well, all the current's going through my Stokes loop. So it's just the total current. It's the same answer as for the long straight wire. Once you're outside, the inhomogeneity inside doesn't matter at all. Indeed, that I get at that in the electrostatics problems, that once you're outside a charged sphere, it doesn't matter what the distribution is like inside the sphere, because all the charge is enclosed. When you're inside, it does make a difference if there is a functional dependence. Because you remember in that, in that problem, you would remember if it had actually been loaded up. There's a slightly trickier, more advanced you should all be able to do it, but you are asked to calculate, using Gauss's theorem, if the charge density inside is a function of the distance from the centre. So that is the one symmetry that can be solved, is the long straight wire. The other one is the solenoid. Now, a solenoid is specifically there's no expense spared in this lectures, it's like, and I've got a bog roll as well. I mean, we've had a potato, we've cut up a piece of paper, and now we've got a loo roll. I mean, I had to put in a grant to get the bar magnet that I'm going to produce at the end. And we imagine that we've got current flowing around and around. Ooh, just about to unhook my microphone. We've got a current flowing around the surface, yeah? So you do need a certain degree of three-dimensional imagination to do electromagnetism. And that's the reason that I've brought in this very strange little demonstration is we're going to look at the magnetic field outside a solenoid. Now, we've got this situation where we're going to first of all approximate. Again, we're actually already, we're going to do this rigorously on Wednesday, but we're sort of sneaking in already the idea that del dot B is naught. I told you this actually, strictly speaking, the perfect cylindrical symmetry of an infinitely long cylindrical wire or cylindrical beam is more or less all we can really do with Ampere's law, because to solve the solenoid, we're kind of already intuitively using the idea that inside the solenoid, del dot B is equal to 0. In other words, and the only way something that can stay with 0 divergence is if the field lines just ran parallel to the axis of the solenoid. So this is a picture, this is the cross section, and you've got to imagine also, the typical physicist approximation, that we're going to say that the field we know experimentally that the field inside is much larger than the field outside. So we're sort of going to say, well, being as that's we'll take a typical physicist's approximation, we'll say that the field inside is perfectly parallel to the axis and the field outside is 0. It's like the way when we solve a capacitor, we pretend that the field lines are running from one plate to the other. Inside they're completely homogeneous and completely parallel, and outside they're 0. Of course there are some field lines around the edge of a capacitor, but likewise we're going to sort of make the approximation that using our intuition that del dot B is always naught, and if the field lines have got to be parallel to each other inside, and being as outside that they're very, very weak, the field lines, that the field is like that inside and it's zero outside. And so we're cutting down the real problem to that. And as you can see, we're kind of leaving out a lot of the interesting bits, but it enables us to solve the problem very easily. And if we think of that approximation, that's what this figure 15 represents. So now this is, again, the notes are up. I might have time to make some board notes at the end, but it's to be clear what this figure is representing is the most important thing. So first of all, obviously this part of the figure represents what happens if we look end on down the solenoid. We see a bunch of field lines coming towards us. Within that very crude approximation that I described, what the left-hand side of the diagram represents is there is some constant value of magnetic field B0 inside the solenoid. And these dots represent, again, I'm sure you've studied this before, this is the arrowhead coming towards you. These crosses are representing the arrowhead coming away from you. That's the feather of the arrow pointing away from you. And so what they represent is that when I construct, not sure how many hands, could I have a volunteer from the front row? Michael, you can volunteer. Smile, you're on candid camera. Could you just hold these, that ruler there and that ruler there? This is now that Gaussian box that's drawn there. Yeah. So now, if I take the line integral, this is now a Stokes loop. Yeah. And remember that as the current flows round the bog roll, it's coming out towards you. Yeah, through this loop. So the current through the loop is just the number of times the current I flows through here. Remember, there's a lot of windings of wire, tightly wound, and the current is just coming at the top of the loo roll here, is coming just straight out towards you. So the total current through the loop is just N, where if this is the length L, it's N times this. Now my line integral is 0 in this leg and this leg, because the magnetic field lines are pointing this way, yeah? The magnetic field lines are this way, and my ds all along this leg is perpendicular to it. So b dot ds is naught. Same applies to this leg. The b is this way, and the ds is this way. So they're perpendicular, and that's naught. The b dot ds out here is also naught, because there's no magnetic field in this very crude approximation. The field itself is 0, so of course b dot ds is equal to 0. So the only leg that I've got to consider in my Stokes loop in the b dot ds is this straight leg inside the solenoid. But here b is parallel to ds, so thank you very much, Michael. We now have got, coming back to the diagram, that's what the diagram is representing there. Deconstruct that brilliant demonstration experiment. The diagram is now representing, as I go around this Stokes loop, even though inside this bit there is definitely a strong magnetic field, but my ds as I go up here is perpendicular to the B field lines, so that contributes naught, this leg contributes naught, this contributes naught, and inside I could not get an easier integral because B0, the B field is parallel to ds, and so if I've got a length L, the left-hand side is just this one single leg, they're parallel to each other, and B0 is constant, that becomes BDS. I take my magnitude of the field outside because it's constant, B0, and I multiply by the length of the leg. Obviously, if I integrate ds from 0 to L, I get L. So the left-hand side for a solenoid becomes B0L. The right-hand side, glad I got a view graph here because I've actually got the mu0 in this time, is very simple too. Again, remember the geometry. The current is passing directly out through the loop at this point. So if there's n turns in this length L, the total current flowing through is just n times the current. Remember, the current's flowing through each time as it goes through here, 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 here. And again, of course, this is an abstraction. for any real finite coil, I've got to have a pitch. I don't have all the windings on top of each other. It wouldn't be a solenoid then, it would just be a coil. I've got to sort of stretch them out slightly. And so this formula is not true for a loosely wound solenoid, because if it was very loosely wound, there'd be a different component. I'm pretending that the current is flowing in perfect circles and they're all just sort of infinitesimally next to each other. But it flows through n times and there's the current. So this is where there are capital N turns in length capital L. So my B field, after all that, is an incredibly simple formula. We have to think our way to get to it, but it's mu naught times N over L times I. And normally when you write the solenoid formula, you write it in terms of small n, which is the number of turns per unit length in the coil. So the magnetic field inside a solenoid is mu naught times the number of turns per unit length times the current. Now, as I say, we're sort of, in the sense that we're using a little Stokes loop, and we're looking at first of all, the circulation of the B field around the loop, and we're looking at the current through the loop, we're sort of just using Ampere's law. But because we've had to put in at this stage, intuition, I'll show you how to do it rigorously on Wednesday, we're putting in the idea that del dot B is equal to naught to have set up our model in the first place. So it's sort of pure Ampere's law, but it's sort of, we're sneaking in the other law of magnetostatics as well. So rather than burden you with an enormous calculation, which, as I say, precisely what I've explained there, and I think it's nice to see it in 3D rather than, if you just look at that diagram, you think, well, what's that about? It looks a bit confusing. But if you see it in terms of the 3D cross-section that it represents, I think it's quite straightforward. So we've now totally exhausted what we can do with just Ampere's law, which is precisely why we're going to go on and do the vector potential next time. So C, the third case, if you like, case A is we can solve the field outside a long straight wire, B inside a long straight wire or iron beam, C the field of a solenoid. And this is, so C figure 14 for what a solenoid means. I'm sure you probably all know that anyway. It's a tightly wound coil of wire. By considering the Stokes loop shown in figure 15, we find B naught times L is equal to mu naught capital N I. Let's move this up a bit. Where B naught is and I'll put in brackets assumed, we have kind of lobbed it in as an assumption at the beginning of the calculation, is the assumed constant magnetic field strength inside the solenoid. We're also assuming B naught is naught outside. That's an assumption too. N, capital N, is the number of turns in length L. And just to say, this formula, which I'll make equation, I believe, yes, I should be up to 4/6. The final formula we come out with is so easy that it's incredible. This formula is usually written as B naught is mu naught small ni. Let's make that equation 4/7. Always running out of space with the blackboards. Story of our lives here. where little n, excuse me, I just have to take it over to this board to save time, is the number of turns per unit length. And once we get to that point, we've exhausted Ampere's law. One final note, note that the field is the same as that of a bar magnet. Now actually, as I say, I put in for a pretty heavy research grant. I've got a couple of bar magnets in here. EPSRC are so generous. Here we go. A couple of bar magnets. So now you see, I'd just like to mention this before we've still got a minute or two before the end. That I said to you that there's no such thing as a static magnetic situation. There have to be currents to make magnetic fields. And you might have thought, no, Martin is clearly fibbing at this point. What about this? No, I'm not getting an electric shock from this, am I? There's no massive currents flowing here. There's no current at all, and yet it's producing a magnetic field. Now, ferromagnetism is the very last lecture of the course for a good reason. It's difficult. It's deep in quantum mechanics that the coupled spins of the electrons in iron behave as if they were producing a current. This thing behaves, it's not a cylindrical magnet, but you can pretend, it behaves as if there was a surface current going all the way around it. It behaves in that way. So a bar magnet is a situation where deep in the quantum mechanical properties of iron, you've got coupled spins that behave to produce an effective surface current. This thing is behaving as if it's got a surface current going all the way around it. And so if you look at the field here, this is not actually such a bad approximation. The field inside is very large and the field outside is very weak. Just to say, last minute, I recommended the Feynman lectures just to give a plug also for one particular one of the Feynman YouTube mini lectures on magnetism. And the interviewer says to Professor Feynman, when I was at school, one of the things that fascinated me, blue end to blue end, was that funny feeling of squashy repulsion when I move one magnet towards another, and you feel that sort of, a squashy repulsion, and it looks like sort of spooky action at a distance. That there I move my south pole towards my south pole, and you can see you can feel that squashy repulsion. And the interviewer says, could you explain that to me? And Feynman says no. The good bit is that in the next 10 minutes he explains why he can't explain it. Okay, I'll see you Wednesday.